All right, so today's lesson is on isosceles triangle theorem and its converse. I'll remind you what a converse is in a couple minutes when I go on to the back. But first, isosceles triangle theorem. We've kind of talked a little bit about this, like here and there. We know that an isosceles triangle is a triangle where two sides are the same. I think I've also talked about how two angles are also the same. So that's basically what the isosceles triangle theorem says, that if you have two sides of a triangle that are congruent, the angles opposite those sides are congruent. So if you had a problem where you were given this, that these two sides are equal, you could conclude that the angles opposite those sides are equal. So you could conclude that A is congruent to C. And the reason for that would be isosceles triangle theorem. So there may be times in a proof where you're given that two sides are the same. You can mark that two sides in the same triangle, I should mention. You could mark that the two angles are the same, and the reason would be isosceles triangle theorem. So before I do an example of it in a proof, I'm going to show you just like one with numbers. So something like this. See how we have an isosceles triangle theorem. An isosceles triangle right here with the 68. So if those two sides are the same, then the two angles are the same. So this angle would be congruent to this angle. And what we could do is we could subtract 68. We would do ones like this, like earlier. So we could subtract 68 from 180, which is 112. And then these two are the same. So if we do 112 divided by 2, which is 56, that will tell us each of these angles. This is 56, this is 56. So then these are vertical, right? So I could plug in 56 here. So then over here, another isosceles triangle where the base angles are the same. So these two angles are going to be the same. So this is 56. Oh man, I didn't want this one to come out like this. That's okay. So this triangle ends up being congruent to this one. I kind of didn't want that, but that's okay. So then you would add 56 and 56 and subtract from 180, and you'd end up getting 68. So they're not always going to be like that. I thought this was going to be one where like these two were the same instead. So anyway, whatever. So there's the first one example. You're going to do some, your assignment today is like some with just like finding angles and then a couple proofs. So there's that. Let's take a look at this proof down here. So we are given in this one, let me restate the given. CD is congruent to CG, DE. So the given was already marked for you. If you're ever doing a proof and the given is not marked, definitely mark it. So DE and GF are congruent, and then CD and CG. So we're being asked to prove that CE and CF are congruent, which we would have to show that some triangles are congruent first. So my guess is that we're going to have to try to show that these triangles are congruent, this one and this one. The reason why I say that is because they already both have two pairs of sides marked. So chances are like those are the ones that we're going to be able to do. So sometimes you kind of have to take a look at like, do we see this big triangle here? CGD. This big triangle has two sides that are the same. So that makes it an isosceles triangle. So that would mean that two angles are the same. I could mark D and G as congruent because of the isosceles triangle theorem. And that definitely helps us with our goal of showing that these triangles are congruent. So I'm going to list that angle D is congruent to angle G. And again, that would be called the isosceles triangle theorem, because I had a triangle where two sides were the same. So therefore, the angles opposite those sides are the same. Now that I marked D and G as congruent, if you take a look at these little sliver triangles that I colored in, do you see how we have a side, an angle, and a side? A side, an angle, and a side in both triangles. And it is the included angle. Remember, it has to be the included angle for both triangles, and it is. So at this point, I could say that those triangles are congruent by side, angle, side. So let's see. I could say CDE. Triangle CDE is congruent to triangle, it would be CGF. And like I said, that would be side, angle, side. Now that I've shown that the triangles are congruent, all of their corresponding parts are congruent. So I can say CE is congruent to CF. And that would be CPCTC. So there's one way that you could use isosceles triangle theorem in a proof. Do we have any questions about that one before we take a look at the converse on the back? No? Okay. So on the second page of the notes is the converse of the isosceles triangle theorem. So if you guys remember earlier in the year when we learned about parallel lines and we did proofs with parallel lines and angles, we learned what a converse was. So in case you forgot, a converse is when you flip the if and the then in a theorem. So the isosceles triangle theorem said, if two sides are congruent, then the angles are congruent. So the converse of that theorem would flip it. And instead of saying if two sides, it's going to be if two angles. So this time you're given two angles are congruent. So if I gave you something like this, and I said that P was congruent to R, you would be able to conclude that the sides are now congruent. So if two angles are congruent, then the sides opposite those angles are congruent. So you would be able to conclude that these two sides are the same. So an example, you zoom in here with algebra would be something like this. Do we see how this is blurry? This is an isosceles triangle, and I know that because these two angles are the same. What is it doing? It keeps like trying to focus. Okay, there we go. These two angles are the same. So based on the converse of the isosceles triangle theorem, I could conclude that these two sides are the same. And then I could just set them equal to each other. We don't really need this 4x plus 16. That's just kind of there as a distractor. So we figured out that these two sides are the same. So then you would just set them equal to each other. And solve. So I'm going to subtract 3x, subtract 2. So I'm going to have 11 equals 2x. So x equals 5.5. Oops, can't see what I'm doing. So that's that, and that's the converse of the isosceles triangle theorem. So again, that's when you're given that two angles in the triangle are the same, and then you are concluding that two sides are the same. Okay, let's take a look at this proof. So we are given, what's the given? That angle 1 is congruent to angle 2, and angle 3 is congruent to angle 4. So let's mark it 1 and 2. And then 3 and 4. So this is interesting. These are not in the same triangle. Oh, actually, yeah, they are. They're both in these triangles. So see this one and this one. Actually, I just saw a different way that we could do this without using isosceles triangle theorem or the converse of it. So I'm going to ignore that method that I just thought of in my head. And we're going to go with the first way I was going to do it. So let's look at what we're trying to prove. We're trying to prove that PT, this, is congruent to this. So you want to take a look at the different triangles that those are in. Those are in this triangle and this triangle. They're in this triangle and this triangle, and they're in this triangle and this triangle. So that second method that I was just talking about definitely can be used. Maybe I'll share it with you after, but let's first think about why do you think they gave us that 3 and 4 are congruent? Do we see how 3 and 4 are in this triangle? So do we see how, like, if 3 and 4 are equal, then TR and RX would be congruent because of the converse of the isosceles triangle theorem? So if you look at triangle TRX, 3 and 4 are the base angles in that triangle. So we could say that TR is congruent to RX by the converse of the isosceles triangle theorem. So that's what I'm going to do next. TR is congruent to RX. And again, that's the converse because we were given the angles and we marked the sides. Okay. Do we see how, if we're trying to show that this and this are congruent, we could focus on this triangle and this triangle? We already have one pair of angles and one pair of sides in those triangles. Then we can mark these vertical angles, right? And then we'll have angle, angle, side, and then we'll almost be done. So that's what I'm going to do next. I'm going to say angle PRT is congruent to angle LRX. And that would be vertical angles theorem. Now we have enough information to say the triangles are congruent by angle, angle, side. Angle, angle, side. So I noticed a lot of you were mixing up angle, angle, side, and angle, side, angle. In order for it to be angle, side, angle, the marked side has to be in between the two angles, which this one's not. So that's how I know. And then we need a congruent statement. So I can say triangle PRT. I can do actually the same here, from one arc to two arcs to none, and then one to none. So LRX. And so that's angle, angle, side. And then lastly, we can say that PT is congruent to LX, and that's CPCTC. And so that's it for that one. So really the new thing here is just using these in proofs, really, because we've done them like algebraically, but not really like in a proof. So just look for triangles where, you know, two of the angles in one triangle are congruent to each other. You could say the sides are congruent. And again, that's the converse of the isosceles triangle theorem. And then the regular isosceles triangle theorem is when you're given two sides are congruent and then you're listing that two angles are congruent.